So the final video for this little booklet has to do with quantitative analysis. So we're on technically, I think it's page something like 38 in booklet 17. And we're going to go through the process of calibration curves. So if you're going to take one thing away from this entire little subunit, I want you to take away how to make a calibration curve and how to use a calibration curve, because that is directly going to help you for next year's course. So to begin with, when we look at quantitative analysis, what we need with quantitative is we need numbers, don't we? So we're looking for a concentration. So we're looking for a concentration, that's the number we're hunting. So to find the concentration of an unknown substance, I'm reading along your notes now, a UV visible spectrometer can be used. In similar to the colorimeter, however, it's got greater accuracy because we now have not just visible light, but also UV light as well. So we've got this greater kind of range of wavelengths that we can use, and so therefore this is a more accurate machine. So let's have a look at the process for creating one of these. So this is the product. This is the calibration curve, and you can see that there are a bunch of those yellow dots along the way. So each one of these yellow dots represents a standard solution. So that is something of a standard solution. So that is one of a known concentration. So you prepare it and you go, okay, I know exactly what the concentration is of this because I've used my stoichiometry and I've added this much mass of the compound to this much volume, so I can figure out what my concentration is. So what we do is we prepare, so when having a look here, there are 3 dot points for under calibration curve. So the first thing you've got to do is you've got to prepare your standard solutions. So these are accurate, known concentrations. Standard solutions are then put one by one into your UV vis spectrometer. Okay, so you would put in this solution and you would measure its absorbance. Yeah, so that solution there, we know it's got a concentration of 10. We know this one's got a concentration of 20, 30, 40, 50. Okay, so that's where the known concentration, and we measure this off the UV vis spectrometer and we plot a point where they meet. So the next standard solution goes in the machine. We know it's got a concentration of 20 milligrams per litre. And then we measure across here and we go, okay, it's reading out an absorbance of 0.11. So I'm going to plot that point there. We're going to do the same thing with so now we put in the third solution. So this is the third standard solution. It might have a concentration of 30. Its absorbance reads out as 0.15. Yeah, and you plot a point there. We're going to do it with the last 2 solutions. So you do it again. You know that the concentration is here, so you know its value on the x-axis, and then you can read the absorbance from your UV vis, and you do this. So what you do is you plot all 4 or 5 or however many standard solutions, you plot them as dots, and then you join them with straight lines. Okay, so you're going to join with straight lines because this is continuous data. What we're doing is we're presuming that if you were to fall anywhere between, say, this point here and this point here, then you must fall on this line. So depending on what your absorbance is, let me just clear these pen markings. What we can do is we can use this to identify the substance. But this is what we call a calibration curve. So to begin with, get your standard solutions that you know their concentrations, measure how much they absorb in the UV vis machine, then you plot them. Okay, there's your 3 steps. What you're going to do now is you're going to use this calibration curve to identify an unknown substance. So what you do is you put in, here's a calibration curve. You can see that the black dots were the standard solutions. And what we did is we put it in the UV vis spectroscopy machine and it measured out as something like 6.8 absorbance. So what I do is I get a ruler and I draw a line across until it intersects with my calibration curve. And then I draw a line down until it intersects with my x-axis. And I can see here that the concentration is not quite 20, I'd be thinking it's about 19 ppm. So it just depends on what, it doesn't matter what your x-axis is, what units are on your x-axis. That depends on what standard solutions you put into your UV-Vis machine. What you are looking for is what absorbance you have for each standard solution. And then once you've got those absorbances, you plot your calibration curve. Once you've got your calibration curve, you can then put unknown substances into it. So in your notes here, it says the substance, you're going to put the wavelength with the maximum absorbance by the substances selected. So when no other substances in the solution will absorb this wavelength. So that's kind of a making sure that you're not got interference. The UV-Vis spectrometer then measures how much the absorbed light is. So that's what I was saying here with the 6.8. Then we compare that absorbance to our calibration curve, and it gives us the concentration. So I would say the concentration of this substance is going to be 19 parts per million. So you're not doing it based on sight, you're doing it based on absorbance in this UV-Vis machine. So what are we going to use this for? So there's a few applications that we use UV-Vis for. A lot of it has got to do with pathology. Now, you may have heard a bit about pathology this year, but pathology is like the testing of urine and blood and bodily samples. So what we can do as hospital pathologists will measure your blood or your urine for the presence of particular substances. So they can use it qualitatively just to measure whether or not it's there. They can also use it quantitatively to see what concentration that might be. So it might be sugar in your bloodstream. They might be looking for how you're coping with different levels of glucose in your system. You also can use this to determine the amount of coloured dye there is in plastic. So that can be helpful if you're trying to economize and make sure that you only use the amount of dye that you need. You can also use it to check for metal ions in a particular substance. So it might be in a waterway. You might want to check what the presence of metal ions is there. You can also look for levels of nutrients, levels of additives, any contaminants in water. And also you can use it for a quantitative analysis of DNA and proteins. So it's more than likely that they're actually using this to do some of that sewage testing. Delightful sewage testing to do with COVID-19 as well. They could be using a technique very similar to this to be looking for it, looking for a signature for a particular piece of viral DNA. But there's a lot of uses of this technology in chemistry and beyond. And that's it.